Let's start from the top. So why this whole paper is about, I mean, these notes are about quantum fidelity, right?
Mm-hmm.
So it's about how similar are two quantum states.
Yeah.
And when we talk about how similar they are, it's about the information in the system, like stuff we can measure, like momentum, energy, that kind of stuff, right? Like how similar these two are.
Yeah, I think in this way, we can even make it simpler and
Okay.
just focus on statistics. So
Okay.
we can make it more abstract and just say something like, when we say information in a quantum state, we're talking about something like a random variable, where a random variable is just a set of possible outcomes and a set of probabilities associated with each outcome, such that the sum of the probabilities equals one. So it's
Okay.
just like flipping. So in other words, it's just the generalization of the idea of flipping a coin. You have a coin, and say it's not a 50-50 coin, and say
Okay.
it's like an 80-20 coin.
Mm-hmm.
So it has so what you have is a random variable would be it can land heads, it can hand tails. There are two possibilities, and then
Mm-hmm.
the probabilities would be 20-80.
Okay.
Um, and when I'm talking about information of quantum state, it's the case that the way quantum states function is, I would say, they're a bundle of statistics, because the mathematical structure is that you have the quantum state, which is a vector and Hilbert space. So if you ever hear someone say it, like the vector and Hilbert space, and hold on, let me get the dog out of here. I got rid of that toy. Sorry, Murphy. He's gonna be bored now. Now he's trying to bite me. Hey, hey, hey. Now he's trying to use me as a chew toy. What was I saying? Yeah, so it's a bundle of statistics.
Mm-hmm.
So you have the quantum state itself, and then you have observables.
Yeah.
And these are Hermitian operators. So if you remember from quantum, these are Hermitian operators, and so these are the set of possible outcomes. So if you have, like, it can be up or down. So if you're saying, like, okay, well, the observable associated with this is that I make a measurement of this, and it can either measure up or it can measure down.
Yeah.
Yeah. And so each one of those basis vectors, you can take one of them and you can apply it to the quantum state, and it spits out a probability.
Yeah.
And so when you look at a spectrum, so when you look at an observable, the set of all of its possible outcomes creates a spectrum. And so if you apply each one of those possibilities to the quantum state, then that would be like your random variable, like the possible outcomes, and then the application of it are the probabilities, and that's given by the Born rule, which is one of the fundamental postulates of quantum mechanics.
Yeah.
So essentially, what you have is this thing for which you can drag out a bunch of random variables. Like, depending on your observable, you can create a classical random variable. And so when I say the information contained in a quantum state, because there are all these different observables and all their bases span the space in a different way, all of these observables are algebraically related to each other. And so the space of information of the quantum state is the space of all of the classical random variables that can be generated by applying the bases of the observable to the quantum state.
Okay.
Does that make sense?
Yeah. This is what gets me confused, because sometimes there's like classical statistics that are in quantum mechanics.
Yes. Yes.
So it's like, yeah, that's what I'm trying to wrap my mind around. Like, what makes it quantum in this case? That's not just like classical statistical mechanics.
What makes it quantum is like the structure of this vector and Hilbert space. Like the mechanics that I just described to you, those are the quantum mechanics. Like those are, and so what makes it quantum, I would say, like, I remember my friend Shelton once said that information theory is applied probability theory,
Yeah.
and quantum information theory is algebratized classical information theory, and it's the algebraic structure. That's what makes it quantum. It's the algebraic structure. It's the fact that you have, for these observables, you can do a change of basis. So,
Yeah.
so I can take a quantum state and I can represent it in the position basis, or I can represent it in the momentum basis.
Yeah. Yeah.
And then there's a Fourier transform that allows you to go from one representation to the next. So it's the different it's the algebraic structure of the space that allows for basically the capacity to interpret
Yeah.
and so what really makes it quantum then is that now that you have this idea of these different languages, these different bases, like if you take the Pauli spin matrices,
Yeah. Yeah.
so you can measure spin in the z direction, the x direction, the y direction. What really makes it quantum then is the fact that you have a Heisenberg uncertainty principle.
Okay.
And so what that means is that if I'm going to measure the spin in the z direction, and then I want to measure it in the x direction, then if the state is along the z direction, so we know the state is aligned along the z direction, but I want to measure it in the x direction, the x direction is orthogonal to it. And so with that orthogonality, knowledge or knowing in the z direction turns into full-blown uncertainty and randomness in the x direction.
Mm-hmm.
And so what happens is that the capacity to which you can know something in one direction they're bounded. So you have this bound on how much you can know. So this is the Heisenberg uncertainty principle. So it's the algebraic structure, which then allows for these mutually unbiased bases or the Heisenberg uncertainty principle, which then, like I was saying in the Anton Zeilinger thing, it's like this idea of information being created. Like in the video that I did on my interpretation of quantum mechanics, I talk about the fact that there's only Anton Zeilinger's idea is that for a two-level system, it only has one bit of information in it.
Mm-hmm.
And so one bit of information can give you a correct answer with certainty to one inquiry. But because of the algebraic structure, there are three inquiries. I can make a measurement here, measurement here, I can make a measurement here. And so all of those inquiries, because there's only one bit of information, then there's an inherent uncertainty. And that's why when you go from here to here, it goes from knowing to completely random. And that's the fundamental quantum nature.
So he's trying to explain like why the Heisenberg uncertainty principle exists.
Yes.
Okay.
He's trying to explain why there's an inherent level of uncertainty in quantum mechanics, and that's the nature of quantum mechanics. It's inherently probabilistic. So it's like we're trying to give an origin for this inherently probabilistic, uncertain nature of quantum.
But why is it that he said he came up with that conclusion like that? Like yeah, exactly. Like why did he come up with that conclusion? Like what?
Yeah, if I remember correctly, it was a proposed principle.
Okay.
So he makes an argument about, let's see, the minimal inquiry. So he first establishes the idea that knowledge comes from measurement.
Okay.
So we make observations, which then allows us to create propositions, assign truth values to propositions about the character or nature of something.
Okay.
And so he's trying to imagine the simplest system you can imagine, and that is a system with a single proposition of either being like yes or no or wrong or right. He proposes the smallest minimal system for which a proposition or character can be had is a two-level system. And I think that's just like a suggestion for a principle. I'm trying to drudge this up, but I think that he then looks at the smallest two-level system that we have in quantum mechanics with the assertion that it still can only have a single bit of information. So it might be something. Well, he makes that argument, but then he demonstrates, I think, how entanglement can be explained with this. So he introduces this principle, and then he uses its logical consequences to observe the nature of quantum. And I know that he has another paper that I read a few years ago where he makes these ideas more rigorous, and that was actually something calculable and something measurable. So it's not just he pulled it out of his butt. It's a pretty good idea, but I need to refresh myself on the exact details.
Okay. So now we're at quantum fidelity, and then in your notes, what you're saying is basically you're tying in like ignorance to a volume, right?
Oh wait, so are you going to quantum fidelity, or are you going to
the notes that you made?
Yeah. Well, I mean, the ignorance to a volume, like that's pretty far in. So the surfaces of ignorance, they arose from me trying to study a quantum fidelity, and the nature of the surface of ignorance and fidelity is that if you have two quantum states and you're trying to find out how similar the information is inside of them, then one of the definitions is to construct their surfaces of ignorance.
Okay.
And then where every point on each manifold is a pure quantum state. And then you want to look at the overlap between quantum states, and you want to maximize the overlap. And then so it's the maximum overlap, the inner product between the pure states on the respective surfaces of ignorance would be the fidelity.
Okay, and this makes the math easier, right? When you do a purification for each state before.
I don't know if it makes the math easier. There's like 4 or 5 different ways of describing the quantum fidelity.
But then between two pure states, it's the easiest, like mathematically, right?
Oh yeah. So yes, that's correct. So yeah, so this is going back. So what it is that quantum states themselves can either be pure or mixed.
Okay.
And so if you have 2 pure states and you're comparing their fidelity with respect to each other, then you don't need to create any surface of ignorance or anything. You just need to take the inner product.
Product. Then the very simple equation.
Yeah, it's literally just it's just an inner product between
Yeah.
2 vectors.
Yeah.
Yeah, the
So
dot product.
two pure states, and it gives you the fidelity, and that means like how similar they are. Like it's okay.
Yeah, yeah,
Uh,
yeah. I'm sorry. Go ahead.
yeah, and like high fidelity means that they're very similar, and low fidelity means they're not. But it gives us, so fidelity gives us, it adds information to the system, right? Now that we have a measure of how similar these two states are. So now we have added information to the system as well, right?
I don't know if we have added information. In the examples I did in the notes, the way I think about it is you can so imagine that someone has prepared a quantum state. So Alice has prepared a quantum state and she sends it to Bob.
Yeah.
And so Bob is down here and he can make measurements. So he can take his observables and he can make whatever measurements he wants.
Okay.
And so if they do many trials where Alice prepares the same state and sends it to Bob,
Okay.
then if Bob were to pick a particular observable and make a bunch of measurements, then he would get a classical probability distribution of what's likely to be observed based off of the information that he knows of the quantum state. So in other words, Alice is like, hey, Bob, I'm going to prepare this state. She tells Bob that. Bob goes, oh, I know which state she has prepared, so I'm going to use the information associated with that quantum state to make predictions. And his predictions will be consistent with observation because he knows which quantum state is being sent to him. So he's using the information of this particular quantum state. Now, imagine instead that Alice sends a quantum state, and now there's a projector, there's like a filter. And this filter represents the quantum state that you want to compute fidelity for. So what happens is that when the state goes through the filter, let's see. Let me see if I remember this correctly. Okay, I think this is correct. When the state goes through the filter, it gets transformed, it gets projected into the filter. So you had its original state that Alice sent, it goes through the filter, and it comes out as this quantum state, not the one Alice sent.
Okay.
But Bob, he's down here, and he still is using the information from the quantum state Alice sent.
Okay. Yeah.
And so what that means is that the statistics that Bob is using to make predictions is different than the state he's actually measuring.
Yeah.
And the fidelity would tell you to what degree does Bob's predictions align with observation, given the fact that he's using the information of one quantum state to predict the outcomes of this quantum state.
Mm-hmm.
And if the two states are identical, then when it moves through the filter, it comes out the other side unchanged, and every prediction that Bob make would be correct because he's using the correct quantum state.
Mm-hmm.
And so the reason why I formulate it in this way is because this projection idea accounts for all of the statistics associated with the algebra of possible observables, as opposed to saying something like because essentially what you want to think of it is you have a bunch of classical probability distributions associated with each quantum state. I have my quantum state here, and then I have a one observable that creates a classical probability distribution. I have another observable that creates another one.
Yeah.
And so in other words, if I have quantum state 1 and quantum state 2, and I have my set of observables that you can imagine a chart, column 1 is quantum state 1, column 2 is quantum state 2, and then across in each row is an observable, then when I construct the classical probability distribution, I'll have one distribution here and another distribution here. And then I go down, and then I have all these distributions. And so that's what I mean by the information contained in it. It's like, let's take the set of all possible classical probability distributions that can be extracted from a quantum state and ask, in totality, how similar is the information across all of them, as opposed to doing what would you do in classical fidelity is you take two classical probability distributions and you look at their overlap by looking at how similar they are, doing an inner product.
Okay. And like when you say filter, what do you mean by that? Like in real life, if that were to be the case, like, well, what is that filter?
Yeah. So quantum states, when we say that they are vectors in Hilbert space, they are also what we call projectors.
Okay.
So if you remember, and I think I have it in those notes I sent you. So think of it as just as a real world example in terms of like a polarization filter.
Mm-hmm.
So say that you send some sort of light through a polarizing filter, and then so the polarizing filter, it cancels out all light that's not consistent with the orientation of the filter. If I change the orientation of the filter, then I change the light that comes out. So I have a bunch of different light,
Okay.
polarized light, and coming through, and then it comes out, and then the only light that comes out is the one that's aligned with the filter. Uh, and so, in that sense, this is a projection. You're projecting out the things that aren't consistent with the filter. And so, quantum states are also like that. Like they can also function as projectors that project out the thing that's not consistent with the filter.
Okay.
Yeah,
That can be done experimentally.
yeah,
Okay.
yeah. And yeah, and so in this sense, the what I'm saying is that you're taking basically the quantum state, you're putting it through a filter, and what comes out is only the things that are aligned with this quantum state.
Okay.
Yeah. And I think in the notes I make an argument that I got out of, I mean, it's just a basic argument that any quantum, like any pure state, can function as an eigenbasis in some observable that spans the space.
Okay.
So yeah, so that was a description of pure, like that's a description of comparing two pure states.
Mm.
And I don't think so far I've told you what a pure state is. Do you understand what a pure state is?
I know it's in like a superposition, right? That's what creates an interference patterns in quantum mechanics, right?
So a pure state itself, whether or not it's superposition, depends on the basis in which you measure.
Okay.
So like I was just saying, like you can always take a pure state and have it function as an eigenbasis, which is the set of possible outcomes for an observable of some observable, in which and so as such, you can always make your measurements in the basis in which this object is pure. And so in other words, what I'm saying is something like this. Yeah. Can you see that?
Yeah.
So you have some observable A.
Yeah.
Here are its eigenvalues and its eigenvectors.
Yeah. Yeah.
You can write the identity operator in
Yeah.
terms of that basis of the eigenbases.
Yeah.
You can apply the identity operator to a quantum state,
Yeah.
and it unfurls it where this becomes the component of the vector, and then this becomes the basis vector. So you're representing the quantum state in this basis.
Okay.
And so this right here is a superposition.
Okay.
And that's because the basis that you're representing the quantum state in is associated with this observable.
Mm-hmm.
But if you represent the quantum state in a basis where, if you represent the quantum state in a basis in which the state itself is an eigenbasis, then everything. So yeah, let me write that. So let's say we have observable B, which is the sum of. My notation is going to be terrible, but I'll see if I can make it not so bad. Yeah. Okay, that's not bad. It's not bad for notation on the fly. All right, I'm gonna write it out explicitly. So okay, yeah, okay. So now we have operator B,
Okay.
and so this is the eigen. So this is the representation. This is eigenvalues and its eigenvectors. So I split this where I write psi parallel. So these two lines represent parallel. And
Okay.
then all of these are the rest of the eigenbases. Now, the thing about these eigenbases is they're orthogonal to each other, so they're
Okay.
perpendicular to each
Yeah.
other.
Yeah.
So because there's an observable like this, then I can write down its identity in the identity operator like this. And I can explain to you why the sum of the eigenbases of an observable is the identity operator. I can explain that to you.
Okay.
So this creates the identity operator. So then I apply the identity operator to a state psi parallel, which is an eigenbasis of this, then this just gives you one because it's inner product of itself with itself, so it is itself. So this
Yeah.
goes to one, and then all of these other things are perpendicular. So the state you get back in the end is simply equal to psi parallel. So you just get this back, which is not a superposition.
Okay.
So what happened is that in this situation, the like this is the nature of quantum mechanics. Superposition depends on perspective. It depends on how you represent the state. If I represent the state using eigenbases, for which the state itself is not an eigenstate of this, then it will look like a superposition.
Okay.
But if I represent the state in a if the state itself is an eigenbasis of the observable, then it's not a superposition. And so this is exactly what happens with the block sphere examples that I've been doing in my videos.
Yeah.
Where when the block when the measurement device is oriented in the same direction as the quantum state, then the quantum state is in an eigenstate and of the detector. And so in that case, you get measurements with certainty.
Yeah.
You get certainty when your measurements. And this is what happens after a collapse. When you have a collapse itself is I can have something in a superposition, I make a measurement, and then it collapses it into an eigenbasis.
Mm-hmm.
But whether or not the superposition is observed completely depends on your orientation. That's why, and this goes back with the other thing, that's why when you have the z direction, when you're making a measurement, and then I make a measurement in the x direction, no superposition, superposition. No superposition, superposition. So it's all about how you represent the state.
So it depends on your perspective. That's where the perspective thing comes in.
Yes.
So pure states are not always associated with superpositions, but pure state different from a mixed state is based on we can have full information about the system in a pure state.
Yes, but full information is different. This is something I thought about for a while, and I remember having a frustrating conversation with a couple of my colleagues once, in which they just were not understanding the question, and it was actually shocking to me the degree to which they had not thought about this. And this is something that I've observed with physicists and stuff, is that you would be surprised and shocked how extremely intelligent people do not think deeply about things. And it's not that they don't think deeply about things, because these people that I'm talking about are probably way smarter than I am. I mean, they're absolute geniuses. But they think very mechanically. Like they basically almost treat the textbook as gospel, and they don't dare wander outside the textbook. So they don't allow themselves to think about things that aren't like given down from on high a lot of the times. And they do, and they rely, everything they rely on is on calculations. So everything has to be a calculation. They don't just process things like logically a lot of times. And so I remember being very frustrated with this because because the thing about quantum mechanics is that a pure state has zero entropy, right? But we know that quantum mechanics itself is inherently described by a lack of certainty. That's the whole. It's probabilistic. That's the whole. Exactly. That's the whole thing about it.
Pure state, we can have full information about the system, but then how? Yeah, keep going. This is my question.
Yeah. And so I remember asking this question, and people were just like, "Oh, well, you can change the basis in which it's observed," and it's like, dude, that is okay. Yes, there exists one basis in which I can make a measurement that is certain. But if I choose a different basis, then the measurements are in a superposition and they're not certain. So that's precisely what it means for a state to be pure or have zero entropy in quantum mechanics. It means there exists at least one basis that I can make a measurement in which the outcome is certain. That's it.
Oh, at least one. It's not all the time.
It's at least one. It's the one that I just showed you.
Exactly. Okay.
it's the one that's consistent with the state itself. Because the state itself, it is a vector in Hilbert space, but it's also a projector.
Yeah.
You can treat it as a projector because, So that's what it means. And so there exists at least one measurement for which the outcome is certain. And so what this is associated with, another way to look at it, is when Alice is sending Bob a quantum state, and she's sending the same quantum state every single time, then Bob knows with certainty that the observations, the statistics of the observations that he's observed, will be consistent with the knowledge that he has. So he has a vector in Hilbert space, and he's using that vector in Hilbert space to construct classical probability distributions to make predictions. And so he knows for a fact that the statistics of the observations that he sees is going to be consistent with this vector in Hilbert space that he has. So that's what it means to have perfect knowledge, or for its state to be pure. Bob knows with certainty which state is responsible for the statistics of his observations.
Okay.
And so this is in contrast to a mixed state where Alice can have, like, say instead of sending Bob one pure state, she has like 3 different pure states.
Yeah.
And so the experiment can have like 100 trials or 1,000 trials.
It's coming from.
He doesn't know which one it's coming from.
That's what a mixed state is. Okay.
Yeah. So
Mm.
in other words, he's down here and he's like, okay, I know that Alice is going to send me a quantum state, and I know that she sends this quantum state 10% of the time, this quantum state 20% of the time, and this quantum state 70% of the time. And
Okay.
so now when I'm making measurement statistics, it's like I don't know which one of the quantum states is coming down, and so I'll just use this one 10% of the time, even though on one trial she might have sent quantum state 2, but I'm going to use quantum state 1 because 10%, 80% of the time she uses quantum state 4, so I'm going to use that one 80% of the time. And so what you get is a probability distribution that might not be consistent with the actual information, the actual statistics that Alice is sending him. Now, if Alice were to call Bob and tell him before he makes each one of his measurements, hey, I sent this one this time, this one this time, this one that time, then he'd be back in the pure state situation.
Yeah. Okay. So I see. So they're both quantum states, but it's just about like a mixed state adds a layer of like even like a classical
Exactly.
to it.
Exactly.
The,
So earlier in the conversation, there was 2 things that you said. You said there's a lot of mixture between classical statistics and quantum. What makes the quantum?
yeah.
So the quantum is the algebra with the Heisenberg uncertainty principle and all that stuff that I explained. The classical has 2 parts. There's the classical probability distributions that are extracted from the quantum state using the eigenstates of the observables. And then there's also the ability to layer a quantum state with classical statistics in the way we just described.
Yeah.
So that's our classical statistics emerges in both.
Yeah. I think for someone coming like studying quantum mechanics as a big, like just like me, like that's confusing at first.
Oh yeah. Well, in quantum mechanics, usually in undergrad and even I don't even think in grad school they do it much. They almost entirely use pure states. They're using like some sort of pure state where you can extract the wave functions out of them. The actual use of mixed states is really relegated. Like I started using it most when I started doing quantum information theory, and that was after I graduated with my PhD. So you might not actually ever really spend any time with density operators and mixed states in undergrad and grad school.
Yeah, because this is all new to me.
Yeah, but I don't even know why though. It's not even hard. Mathematics is not more difficult.
Yeah.
Yeah.
And then let's talk about purification. So purification is, that there's this concept of like tracing, as if like the quantum state that we have is part of a bigger quantum system. From my understanding, that's how it is. Like I don't know, this concept is so different from like the classical world. Like where is it coming from, and like how does that even help?
It's entanglement. So earlier I gave you one way in which a mixed state could arise, and that was if Alice sends Bob a bunch of different states with a layer of classical statistics added.
Yeah.
That's one way. The other way is for you to take an entangled quantum pair, like a Bell state, take an entangled quantum pair, split them off, and give someone only one of them. So when you represent a composite entangled state in quantum mechanics, what you can do is you can say, I have a quantum state, a pure quantum state that represents the statistics of the combined system together. But then I can ask myself, well, given this, how much information in this composite quantum state is contained within one of the parts? So you have an actual physical composite system made up of an entangled pair, and then I have a quantum state that describes that entangled pair. And so if I ask the question, what happens if I only measure one? Then I can go to my quantum state, and I can extract the information associated with this one, and that's the splitting. So in other words, when you're looking at a mixed state, is the result of taking a composite object and splitting the quantum state to have the information only associated with one particle.
Okay.
So what this means is that the degree to which you are missing information about a state, in other words, when I do the splitting, how mixed is this? How much information do I have? If the thing is really mixed, then that actually tells you how entangled they are.
Yeah.
And I say this because think of it this way. because this is a definition of entanglement in terms of separability. So you can have two different types of composite systems. I can have a composite system in which the states are separable, which is to say basically I prepared one state over here, I prepared one state over here, and they have nothing to do with each other. They have no correlations at all.
Okay.
Then I can create a state in which I prepare two things together and they're entangled with each other. In the case in which they're not, which they're completely separate, then you can think of both of these things as having a complete information about themselves separate of each other. They have nothing to do with each other. And so think of it as writing a letter, where you write a letter, you have a piece of paper and you take the paper and you split it down the middle. Right? I write one complete letter on one side and one complete letter on the other side. So when I rip the thing in half and hand it to you, you have two complete letters with no missing information.
Mm-hmm.
But if I were to take the letter and go down the middle and I would write it across the center, and then I ripped it in half, then all the information about this particle is over here and it's lost.
Mm-hmm.
And so now you have an incomplete letter. That's entanglement, because the entanglement is that the information is entangled with each other.
Okay.
That's what quantum entanglement is. And so that ripping of the piece of paper so that the information about the other particle is lost, that then becomes a mixed state for an observer who's only measuring that one particle.
Mm-hmm.
So the degree of mixedness of a state is actually a measure of entanglement. And so what that means is that mathematically, if I ever have a mixed state, then I can assume that mixed state came from an entangled pair, and that the ignorance associated with that state.
Say that again.
If I have a mixed state, so like if I have a quantum mixed state, then I can always assume mathematically, this is what purification is, I can always assume that thing came from a composite system.
But see, this is my problem. It's like the assumption seems like a mathematical trick, like how can you just assume that?
Well, the reason why is because the ignorance that Bob observes, whether it's done from Alice mixing or whether it's done because he only has one part of an entangled pair, is indistinguishable.
Okay.
In other words, if you just had the mixed state, you wouldn't know what caused the ignorance. The ignorance itself is indistinguishable.
You don't know where it came from at all.
You don't know where the ignorance came from.
Okay.
So if all you knew is that someone was sending you a quantum state, and this was the mixed state that contains the information about it, and they didn't tell you how they produced the mixed state. They didn't tell you that Alice was up there mixing stuff together, or they didn't tell you it came from a split entangled pair. You don't know. It's identical. You can't distinguish it.
Okay. But then how does that help in any way? Like, okay, we don't know. So what's the next logical step? Is the assumption that it's entangled to another state? That's the next assumption?
Yeah. Think of it this way. It's a difference between subjective ignorance and objective ignorance.
Okay.
In the case where Alice is sending Bob the quantum state, you have to think that there is a classical environment, which is the laboratory. So Alice and Bob are both in the laboratory together. And so you have this classical environment that both Bob and Alice are entangled to. So they have a shared reality from this classical environment. So what that means is that Alice and Bob are both classical objects in this classical environment. And so the information about the information that is missing that Bob doesn't have, in principle, he could have it. Because in principle, Alice could pick up a phone and call him and tell him.
Okay.
So his ignorance isn't due to an objective loss of information. It's due to his subjective ignorance.
Okay, yeah.
But in the case of entanglement, it's the case that what you have is something like a separation of realities, where you have the actual laboratory, but then you have your quantum state, and it's actually separable from the laboratory. So you have your composite system, which is an entangled pair. But that entangled pair itself, if it's a pure Bell state, this is a pure entangled pair, then that means that thing is not entangled to the environment. So that means that the laboratory environment and the entangled pair, they're in a separable state. You have your thing here, and then you have your laboratory, and they have nothing to do with each other. They're completely separable.
Okay.
But if one or both of the entangled pairs starts to interact with the environment. Like say some photon comes and interacts with it, or something comes and starts interacting with it, then it starts to entangle it to the environment. And so what I'm saying is that in the case of this difference in ignorance between subjective ignorance and objective ignorance, is that when the entangled pair is in a pure state, so that it's completely separable from the laboratory, then that means there's literally no information, there's no correlations between the quantum state and the lab. There's an objective lack of information.
Okay.
It's not that Alice is holding on to it and she could call Bob, or think of it this way. I always think of it in terms of the potential to predict the future.
Mm-hmm.
So to have information is to be able to predict the future. And what that means is that there must be some correlations between the information you have and the thing you want to measure. So an example I use is something like, take a coin and you don't know its distribution, whether it's a 20/80 coin or whatever. And so you want to figure out, okay, what's the weighting on this coin? And so you pick it up, you do an experiment with like 1,000 trials, and you just start flipping the coin, and then you record the outcome on a piece of paper. And so,
sorry to cut you off, Shannon. I forgot I have a meeting right now, 9:30.
oh, okay, all right, well, we can pick it up here. I'll stop this recording.
We can call back in 15 minutes, by the way.
15 minutes? Okay, yeah, that's fine.
Yeah, we can like cut off the video and then like
yeah, that's cool.
Let me just do the meeting quick, and then I'll hop back on.
All right, no problem.
Okay. See you soon.
See ya. Figure 2 and figure 3. Those really, I think, break down the importance of what's going on here.
Okay. Figure 1, each simplex presents a classical distribution.
Oh, are you in mixed state geometry original?
Mixed state geometry original.
Not purification of 3-level systems.
I'm in purification of 3-level systems, yeah.
Yeah. Look at the other one.
You only sent me one, didn't you?
No. Mixed state geometry original. I went to the email and downloaded it. That's the one you should. That's the most important one that you probably should have been looking at.
Mixed state geometry, yeah. I understand that. You explained that.
Yeah.
But you know what? Before we ended the last call, we were talking about purification. I still don't get it. Like the assumption being made. Okay, there's entanglement. Like we want to work with a quantum system, right? And it's a state, and then you want to purify it, right? So there's an assumption that it's entangled to another quantum system. Is that the assumption? And you're saying, and you tied it into the experiment that we don't know where the ignorance is coming from, right? Because like the mixed state is based on ignorance, right? That's the pure state and mixed state.
Yep.
You're like, it has to come from somewhere. But see, like, where is that somewhere that we're assuming and we can do like math on? Like the math seems like it's a trick. Like we're, is it just arbitrary, or like what's exactly happening? Like intuitively, what is happening?
Yeah. So think of it this way. In one sense, if it is the case that the ignorance comes from Alice sending Bob something based off classical statistics, then in that case, the entanglement picture is wrong. Alice, because she's in the laboratory, she could just tell Bob, like, no, that's not an entangled state. That's just me screwing around.
This is what you're saying is subjective versus objective ignorance.
Yes.
That's why you're, okay, yeah, I get it so far.
But if it is the case that you're dealing with entangled pairs, then this exactly maps onto what's happening.
Yeah, but from my understanding, when I was looking into these things, it's like, okay, like they do like a mathematical trick basically, right? So to like the trace when you have a quantum system, and then isn't that arbitrary, or like how do you know what information do you have about the entangled system that's allowing you to like move forward with any calculations? Or
so what's happening? So earlier you asked me what is quantum, like what makes the quantum, and it's the mathematical structure encodes the knowledge that we have about the nature of quantum mechanics. Okay. So the mathematical structure should be a reflection of the nature of quantum mechanics. If it wasn't, then we couldn't use it to make predictions or anything. Mm-hmm. And so when you said like we're taking the trace, we're doing a trick, this is the nature of Hilbert spaces and composite Hilbert spaces and how we represent entanglement. Like when we represent entanglement, we have one Hilbert space, which represents the space for one particle, another Hilbert space, which represents the space of another particle, and they're vectors in that space. And then we want to make a composite system. We take the two Hilbert spaces and we composite them together using something called a tensor product.
Okay.
And so this tensor product, it's like multiplying the states, the spaces together. You're multiplying spaces together. And so now in this composite space, this composite Hilbert space, which is the multiplication of two smaller Hilbert spaces, you can represent states of a system that are two particles together. And so when we're taking the partial trace, we're saying, okay, we have this Hilbert space that we've constructed at these two smaller Hilbert spaces. Now, let's just go ahead and go back to one of those Hilbert spaces, because this composite space is made up of these two spaces. So if we have a state that exists in the composite space, which is the space that describes two particles, and then I ask, well, what is the information I have of just one of the particles? That's what the partial trace does. It takes the object in the composite space and projects it down to the Hilbert space associated with the single particle.
Okay.
So that's just the mathematics. And I think that there is some debate, as I think when you look at the foundations, I've heard Sean Carroll and other people talk about, like, why tensor product? Why are we doing it this way and all this stuff? And that's, I mean, for me, I guess there's an assumption like von Neumann came up with this stuff. He's the one who established the foundations of all these things. I think him and Dirac. So it's like, well, that's you know, what I'm thinking is there's a possibility that there might be some sort of bull crappery going on here that may not be established as like gospel. But I'm functioning in the space of quantum mechanics as it's been given to us by Dirac and von Neumann. Okay. And as far as I can tell, this structure is sufficient for making predictions with experiments. So it's good enough for me.
Okay.
So then for me, now that I'm a theoretical physicist who relies mostly on calculations and I don't like being in a lab, I remember once being in a lab and then being told to couple light to this thing and like turning knobs. And I was sitting there trying to turn knobs to couple light to the thing. And I just started laughing because like, I hate this. This is not why I got into physics. I don't like this at all. So I don't like doing. I'm essentially an applied mathematician.
Okay.
And so when I do physics research, I am functioning within the structure of mathematics that has been established, with the assumption that it's correct. So the partial trace process, you know, is what it is. But this is how we represent entangled states by constructing these composite systems. And if we want to look at one part of the system, then we do these partial traces to go down. Yeah, so that's just what it is.
Okay. And it works, and it's been established in physics.
Yeah.
I understand it intuitively, but I mean, if it works.
Yeah. Yeah, and so here's something interesting. So now that you have this idea of entangled, so I have an entangled system, and I want to know how much information I have about a single particle.
Okay.
And so when I take the partial trace, what I get from the partial trace is the quantum state of a single particle, but it's missing information because that information is contained in this one. It's like writing the letter.
And then the letter thing, yeah.
Yeah, the missing information is the result of the fact that the rest of the information is over here. And so if I compute the von Neumann entropy of this thing that I got from the composite system, then the degree to which it is mixed and not pure is a measure of entanglement. It's saying that
again.
The degree to which this thing is not pure is a measure of entanglement. Yeah. Because remember, a composite system in which they're not entangled, meaning they're completely separable and have nothing to do with each other, is like taking a piece of paper, dividing it down the middle, and writing two complete ideas independent of each other on a piece of paper. If I split that in half, then I have a complete idea. There's not any missing information. And so the amount of missing information is a direct measurement of how much of the information is contained over here, which is telling you the degree to which they're entangled.
Okay.
Yeah. And so the von Neumann entropy of a particle that's the result of a partial trace of an entangled pair is a measure of entanglement. And what it's saying is that it's and we call this the entanglement entropy. Okay. And what it's telling you is it tells you about your potential to reduce the uncertainty of a measurement outcome. So think of it this way. When I was talking about the idea of subjective versus objective ignorance, in the objective ignorance case, the entangled pair itself, like the composite entangled pair, if it's a Bell state, which means that it's purely entangled, it's purely entangled with its pair, then that means that it has no correlations to the environment that Alice and Bob are in, where they're going to make a measurement. So that means that you have think of the environment that Alice and Bob are in as a quantum state, and then think of the entangled pair as a quantum state consisting of two particles. And so the quantum state of the pair is separable from the quantum state of the environment that Alice and Bob are in. They're separable. So they're not entangled. They're completely separable. They have nothing to do with each other.
Okay.
And so what that means is that because there's no correlations between the environment and the quantum state, then that means that there is absolutely no capacity for Alice and Bob to reduce the uncertainty of a measurement outcome. And this is what I was saying before the conversation ended. Before the conversation got cut off, I was saying that to predict the future, that to have information is built to predict the future. And so to do that, you need the information you have has to be correlated to the thing you want to measure. And so the example I was using was the idea of a coin where I don't know what the distribution of it is. And so I do an experiment with like 1,000 trials where I start flipping the coin and then I start recording the outcome. And if I do enough trials, then eventually I'll get some sort of distribution. Well, 80% of the time after 1,000 trials, I saw heads, and 20% of the time I saw tails. So now I know what the distribution is. And so the information that you recorded from the experiment is correlated to the physical coin. Mm-hmm. So now I can use that information to predict what I'm likely to see if I flip the coin. You see? And so the information, by doing the experiment, you've created a piece of paper with a bunch of outcomes on it that's correlated to this thing, which allows me to predict the future. And so to predict the future, you need correlations between what information you have and the object. But if the entangled pair itself is completely separable from the environment, meaning it has no correlations, then what possible correlated structure do you have in the lab to predict the outcome of a measurement of one of these particles? You have none. There's literally no potential or capacity to reduce the measurement of an outcome of a measurement. Okay. And so that's why if you compute the von Neumann entropy of a subsystem of an entangled pair, it's maximally entropic. It has no information. It's maximally entropic, maximally impure. There's no information in it at all. So whenever you take a composite system and you measure the von Neumann entropy of a single particle of that system and it's maximally mixed, then that means that it's maximally entangled.
Okay. And then what follows from that?
So now, okay, so what follows from that is when I have my mixed state, so now we're getting into the purifications.
Okay.
When I have my mixed state, imagine I have a mixed state that's the result of having that's a result of a composite system in which you're only looking at the trace or you're looking at one particle. Then the problem is that from the perspective of this thing, when I look at the purification, so let me step back. When I say that the von Neumann entropy of a single particle is the entanglement entropy, we're assuming that the composite system itself is a pure state. So we're assuming that this composite system up here of a two-particle system itself is a pure state. And when you take one particle and trace it out, then what you have is a mixed state. Mm-hmm. And so the problem is that when I construct the purifications, there are many pure states that could have produced it. There isn't a single pure state. There are many of them.
Yeah.
Which means that because all of these pure states can produce the information you have in the mixed state after doing the partial trace, because there are many of them, then you are ignorant about which one actually constructed that thing.
Yes.
And so so if there's 1,000 pure states versus 1,000,000, if there's a bunch of purifications that could have produced that, if there's 1,000,000, then you're way more ignorant about which one, if you had to guess at random, than if there were only 1,000 or 100. You have a 1 in 100 chance of guessing the right one. If there's only 100, you have a 1 in 1,000, you have a 1 in 1,000,000. So the more pure states there are, the more ignorance there is.
Yes.
And so what I did in my research is I was like, okay, let's take this thing and let's construct the manifold of all the purifications and then compute that thing's volume. And it's essentially like a smaller volume like having 100, a larger volume like having 1,000, and an even larger volume like having 1,000,000. So what that's telling you is that within the composite Hilbert space, because you constructed a composite Hilbert space out of the two smaller ones, within the composite Hilbert space, there is a set. And there's a set of purifications that when I take the partial trace, give me this mixed state. And so the information that distinguishes that set are all of the pure states such that when I take the partial trace, they map back down here. So that's why you have this one thing, you have a branching out
Yeah,
Here,
and you
look at my
said there
notes.
could be many purifications.
Yes, yes.
Okay, and then
And so what this means is that what I found is that if you have a pure state that's already a pure state, so you have the state, you have the space of the composite of the Hilbert space, and then I have the single Hilbert spaces. So I'll ask you, what do you think the volume is for a state that's pure in the single Hilbert space? When I look at its volume in the composite Hilbert space, what do you think its volume is if it's already pure in the single Hilbert space?
no idea.
It's 0. It's already pure. You can't purify it. The process of purification is to construct all of the pure states that map back down to the state in the single Hilbert space.
Okay, yeah.
So if it's already pure down here,
Mm-hmm.
then there's nothing there's nothing to construct.
Yeah, okay.
So it has 0 volume.
Okay.
But as the thing becomes more mixed, as you move away from purity and it becomes more mixed, then the volume grows monotonically. And so you can go from pure and continuously change the state by adding more mixedness until the volumes grow until it gets to a maximally mixed state in which the volume is maximal.
Okay.
And so what that tells you is that the volume is telling you about a measure of entanglement. And what's happening in the composite space is, remember, the composite space is consistent of a set of things. I have a set of purifications that map down to a mixed state. And so imagine that down here, and this is a triangle. So in my notes, I have a triangle
Yeah.
which represents the single particle, which represents the single particle Hilbert space. And the vertices of the triangle represent pure states. And anything that's not on a vertex are mixed states.
Yeah.
And the center of the triangle is a maximally mixed state that has no information in it. And so if I were to look at a trajectory, for like a curve on this triangle from a vertex to the center of the triangle, then what I can do is along that trajectory on that curve in the single particle space is there is a corresponding trajectory in the higher dimensional Hilbert space.
Yeah.
Because remember, at each point on that curve, I can construct a manifold of purifications.
Yeah.
And so what that means is that the composite space itself gets coarse-grained. It gets constructed into a space of disjoint sets where each set corresponds to a point down here. So
Yeah.
for every point down here, there is a unique set of purifications that map back down.
Yeah, I understand that. Yeah.
And so what that means is that when you're looking at the state itself, and it's going from a trajectory of a pure state to a maximally mixed state, then the composite Hilbert space, it's moving from a purification manifold with smaller volume to larger volume. And this is important because this is the nature of the second law of thermodynamics. This is the arrow of time. And this is exactly the argument that Boltzmann made when he was trying to prove his H theorem to mechanically derive the arrow of time, why entropy always increases.
Yeah.
Because these things up here, these purification manifolds, they represent entropy. They're ignorance. They represent the amount of ignorance.
Yeah.
And so what I've done is I've created a coarse graining of the composite Hilbert space that separates it into a bunch of disjoint sets where each set represents the set of purifications associated with a density operator in the base space. Yeah. And so what this means, if you're asking what all this means, is that this trajectory of it going from a pure state to a mixed state can describe an entangling process. Because remember, when something is pure, it's separable. It has no correlations. Decoherence is when it starts to interact with its environment and starts entangling with it. And so when it starts entangling with it, then that purity is starting to be lost and it's starting to become mixed. And so we can get into what this means in terms of information, because it's actually pretty subtle, this next argument. But just now understand that as I go from a pure state to a mixed state, due to the fact that a pure state is entangling to some larger system, then the ignorance that's happening is like the purity of the information is bleeding into the other thing. It's like you had that separate piece of paper that was separate, and then the information starts to mix in, it starts to blend together. And so that mixing results in a trajectory of going from, in the composite Hilbert space, from macro states of smaller volume to macro states of larger volume. So what I've constructed is a description of the arrow of time, of thermalization, purely in terms of entanglement.
Okay.
Does that make sense?
I have to collect my thoughts.
Just ask whatever question, just ask any question, just whatever comes to mind. Don't be afraid to ask anything at all.
I just want to make sure I'm following 100% of what you're saying. Okay. Just going back, just like a quick note here. When you have in your figures, you're like saying the triangle corresponds to like a volume, right?
The triangle in the base space represents a set of density operators. It's a collection of density operators in the single particle Hilbert space.
Okay. And then each point corresponds to a point on a sphere, for example, right?
Well, right now, all we need. So right now, let's just think of the triangle itself. I mean, we can actually take the triangle and we can start doing unitary transformations and rotating it, and then what you said is correct. But we don't need to think about that right now. We just need to focus on the triangle.
Okay. Yeah. Now, so you're saying that the triangle, does it have to be a triangle or any geometric shape? Like
it's a simplex. It's a simplex. Okay. In the higher dimension you go, it's just the higher dimensional simplex.
Okay, yeah. So right now we're talking about triangle. If we go higher dimension, it could be like something else.
Like a tetrahedron or something.
Yeah, okay.
Yeah.
So right now, okay, we're simplex. So each vertex is purification. It corresponds to a purification.
Each vertex in the base space corresponds to a pure state.
To a pure state. Okay.
Yeah. So remember, pure states are the idea of zero von Neumann entropy of a single particle. Purifications exist in a composite space.
Yeah. Okay. Yeah. And then you're saying that this composite space has a lot of possible purifications corresponding to this simplex, right?
Yeah, so for each point on the simplex, there are many purifications associated with a single point on the simplex.
Okay, so that we got that so far. And you're saying if we have a trajectory on the triangle, the simplex, from one point to another. Now, see, like this is something that I struggle with. When you say that, and you and a lot of physicists, they say stuff like this, but what does that actually mean when you move on the simplex? What does that correspond to, like in physics or intuitively? What exactly is happening? Because you can think quick, but what is it actually?
You can think of it as decoherence. And so decoherence is the process where a state entangles to its environment. So the whole problem with quantum mechanics is that you have some sort of state that's pure. And so if it's pure, then you're telling you something. I know, I have knowledge about the statistics of this state. But if the thing starts interacting with its environment, then it starts pinging it. The environment starts pinging it.
Yeah.
That does...
It affects it, basically, right?
It what?
It affects it.
Yeah, you can think of it as that. It affects it, or what it does is it makes correlations between this thing and the environment.
Okay.
And so now it's starting to entangle this. So think of purity as being isolated. That's why it's associated with separability. So entanglement can be defined as a state that's not separable.
Yeah.
If it's separable, then that means that it can be over here.
Yeah.
And so a necessary condition for a state to be pure is that it's separable.
Yeah.
So when it starts to interact with the environment, it's no longer isolated. So it's no longer separable because it's creating correlations.
Okay.
And when it does that, so when it does that, you can think of the information you had about this as bleeding into the environment, because the environment is usually a very high dimension. It's like the entire laboratory. And so whenever the laboratory starts pinging it, the information you had starts to bleed into the environment. Now it's lost. And I'm like, And so it's not that the quantumness is lost. It's almost like it's being distributed or into the room such that I don't, And so that's what's happening. And so as the thing starts getting pinged, it starts going from a pure state, with vertex on the triangle, and starts moving toward the center.
Okay, that's what's happening now. Okay, so we're basically the information is being lost.
Yes.
Okay, that's what's happening. Now, that's another question. Well, why is it that the vertices are pure states? Why is that?
Because the vertices represent a single projector. So remember at the beginning of a conversation, we were talking about pure states.
Yeah.
And we were saying, what is the von Neumann, like what does it mean to have zero von Neumann entropy? It is literally to be one of these vertices. So when you look at the structure of this space is that you have a Hilbert space, which gives you vectors, which are your quantum states. But you can construct a space on top of that Hilbert space of operators. So these are things that can operate on vectors in the Hilbert space.
Okay.
But the vectors themselves can be turned into operators by taking the outer product with themselves.
Okay.
So that's what it looks like this. So this is a vector in Hilbert space,
Yeah,
and
yeah.
this is its projection operator.
Mm-hmm.
So this thing can act on objects in the Hilbert space.
Okay.
So when you're looking at what you ask, why is the vertex pure states?
Yeah.
It's because the vertex represents a vector in Hilbert space with maximum length. So it represents, they call them array. I think that's correct. They call them rays in the Hilbert space. So it's just like the vector itself has a length.
Okay.
And so the length of the vector tells you about its purity. So the vertices are the points with the maximal length. So this goes back to what you were asking earlier about the spheres. Like now we can talk about this. So basically the vertices are like the highest point. You have the center of this projective space. So let me just say that this constructs something called a projective space. But so when you're looking at the triangle, we're actually in the projective space, not in the Hilbert space. We're looking at the space of operators.
Okay.
And so in this projective space where this triangle exists, you have a center, which would be a vector of 0 length. And then you have a point on the triangle, and you have the vertices. And so if I were to measure the length of the vector from the center to a vertex, that's going to be the largest length you can have.
I see. Yeah.
And then any other one is going to have a shorter length.
Okay. Okay.
And so then that constructs this picture that I've shown you of two spheres. One sphere is the outer sphere where all the pure states live.
Yeah.
And then you have this inner sphere, which represents the space where all the maximally mixed states live, which are the maximally mixed states have the shortest length.
Yeah. Yeah.
And then you have all of the and then you have two spheres, maximally mixed sphere, pure sphere, and then all the density operators either exist on this sphere, on that sphere, or in between.
Yeah. Okay. Okay. So we can also say it's like the farthest distance from the center of the triangle, and that's the vertices is the farthest. So that means like we have less mixing, and we get to the purity on the vertices.
Yes. Yes.
Okay.
So that's why the pure states represent the vertices.
Yeah. So and you're saying let's say we do start at a vertex, and then we're going anywhere else inside the triangle. Then you're saying in an experiment that's like decoherence with the environment, and then now we're mixing. Okay. So then what follows from that?
So that process of this thing decohering is a thermalization process. So here's the kicker of all this. So remember I said that you have a triangle in the base space, and then you have a composite space. So keep that sharp in your mind. There are two spaces, the base space and the composite space. The higher dimensional space and the lower dimensional
together, space. Right? They're correlated with each other.
Yes. And this is what's important, is that by doing this, I'm creating a coherent mapping from one to the other.
Mapping.
When I say coherent, I mean the information is preserved from one to the other.
Okay, yeah.
And so by taking a point on a simplex, which is a density operator, and then looking at the purifications in the composite space, I'm creating a one-to-one correspondence between a manifold of purifications up here and a point down here. And so the manifold of purifications, its volume, its size, manifold of purifications, that's a representation of the information of the state in the lower dimensional space.
Yeah.
That's why it's coherent. Like if this thing has less information in it, then this thing is bigger. So the size of this thing is representing something like the coherent mapping of the information down here from a lower space to a higher dimensional space up here.
Okay.
And so what that means is that when the thing is decohering, it's moving on a trajectory in the composite space from manifolds of lesser volume to manifolds of larger volume. And so the largest volume represents a maximally entangled state.
Yeah.
And so what this is an arrow of time that says that if you allow the universe to just evolve, it evolves in a direction of maximal entanglement.
I see. Okay. Yeah.
And so within quantum mechanics, there's a very well-known result that when you look at composite Hilbert spaces, that the vast majority of the space of composite Hilbert spaces consists of maximal entanglement.
Mm-hmm.
No one has an explanation for this until I provided my coarse graining.
Mm-hmm.
With my coarse graining, it explains why that is, because this is an instance of the arrow of time for entanglement.
Okay.
And it's telling you that the arrow of time, the universe tends towards maximal entanglement.
But can't it be explained intuitively? Like, okay, there's more stuff happening in the universe, so then there's more stuff interacting, so there's more entanglement.
Yes, it's like that. It's the likelihood that thing will remain set. It's like if I started off with a bunch of things that are all separated from each
Yeah,
other, and then you allow them to evolve, the likelihood that they're just going to remain separate is poor. Like
yeah,
they're going to start mixing together.
yeah,
It's the exact thing of like taking a container of air and putting all the particles in a corner. That's a low entropy
yeah,
state because But then when you allow them to evolve, they start moving all over the place, and you get something that's really mixed. It's the same thing.
yeah. But
Yeah.
what does that have to do with the coarse graining you're talking about?
The coarse graining is the thing that's associated with increased entropy. So when you go back to Boltzmann's original arguments for
Mm-hmm.
his arrow of time, Boltzmann was trying to derive the arrow of time using classical Newtonian mechanics.
Mm-hmm.
So back then, the thermophysics that's developing, and we're asking the question like, why do we have this entropy generation when we're trying to do work? We have this generation of entropy that's not doing work. It's like a diffusion of energy. It's like, why is this happening? And so you start developing like this idea that entropy always increases. And so people are asking, is that always true? Do we have a basis uh to this idea and something that can be rationally explained? And
Mm-hmm.
so Boltzmann set out to do this. And so he tried to prove something called an H theorem, which was the case that he was saying that there is a quantity H
Mm-hmm.
such that if I have a container of gas, of particles, and I allow these things to just kind of interact freely, then there exists some quantity H that always increases. It never decreases. And that would represent the arrow of time. Like the
Yeah.
thing always increases.
Okay.
And so he set out to model this container of gas as spheres that are interacting with each other and bouncing off each other and interacting with each other. So he makes a bunch of assumptions. He makes a bunch of conditions like the density of particles, how often they interact, the correlation between the particles. Like he makes all these assumptions to then write down a quantity called H and demonstrate that it always increases.
Okay.
But then this guy named Lockschmidt showed up and made and argued against Boltzmann's result because in physics, the equations of motion, the Newtonian equations of motion, Hamilton's equations,
Yeah.
they are reversible.
Okay. Okay.
Meaning that I can take a process, like say I take a process where all the gas is contained in a corner and I allow it to evolve. And then say that after it diffuses and everything's all like nice and uniform, I stop the process and I reverse the momentum of everything. So I take all the momentum, then I reverse everything, and then I allow the thing to evolve according to classical mechanics. Then everything should reverse back and it should collapse back into the corner.
Yeah. Yeah.
And so this is the problem of reversibility. And so this is called the Lockschmidt paradox. And so Boltzmann had to respond to this because the argument is, well, if I have these assumptions and I think that there's this quantity H that evolves, well, because of this reversibility, there must exist a physical possibility of reversing all the momentum and it collapsing back in on itself. So clearly the thing can't always
Yeah.
increase. It has to be able to decrease. That
Uh-huh.
was Lockschmidt's argument.
Yeah.
And so Boltzmann had to make a defense of his claim, and he made it a combinatorial argument. And this combinatorial argument came up with these ideas of dividing up what we call phase space. So the first phase space is the six-dimensional phase space, which we call mu space. And so phase space itself, just to describe that tells you the position and momentum. So going back to Hamilton's equations, in Hamilton's equations, the variables, the dynamical variables for which the evolutions are happening are what we call canonical variables, which are position and momentum. So in physics, we have this idea called Hamiltonian mechanics, and the canonical variables are position and momentum. And when we derive our physical theories, we always have some sort of abstracted version of position and momentum. Like in general relativity, position is the metric tensor, and momentum is the extrinsic curvature tensor.
Okay.
And so we always have this notion of position and momentum. And so the phase space is telling you about is the space of position momentum. So when you want to look at the system evolving, you look at its trajectory through its position momentum. How is position momentum changing? And so if I have a bunch of particles, and they're in a container, then they have 3 degrees of freedom of position and 3 degrees of freedom of momentum. So each particle has an X, Y, and Z in position and an X, Y, and Z in momentum. So that gives you a 6-dimensional space to describe the position momentum of one particle. And so in this mu space, if I have 50 particles, then there are 50 particles in the 6-dimensional space. And the actual evolution of the system would be the changing of the position momentum in this 6-dimensional mu space of every particle. But then you can construct something called gamma space. And gamma space is a 6 times n dimensional space where n is the number of particles. So you have 6 degrees of freedom for position momentum. And then you have dimensions is that multiplied by each particle in the system. And so this gamma space, a single point in gamma space, represents all of the trajectories and everything of a particle in mu space. So in mu space, you have one point in that space for each particle, and in gamma space, you have 1 point for each system. So all the particles get condensed. The information about all the particles gets condensed into one point that is moving along in the 6n dimensional gamma space.
Okay.
And so I'm saying all of this because Boltzmann, to refute or argue against Lockschmidt, he said, let's take mu space and subdivide it, and just make a uniform grid and subdivide it. Okay. And when you do that, then each of the particles of the system is going to fall into a cell, where a cell represents a position and momentum vector.
Okay.
And then and so from this, he's able to make a combinatorial argument where let's say that all of them are in one box and only one of them is in. So there's two cells. All the particles are in one cell, and one particle is in this cell. And because the particles are indistinguishable from each other, I can take one particle, put it back in here, take out another one, and put it in here.
Okay.
And because they're indistinguishable, then that's equivalent. Yeah, that's an equivalent thing. You can't actually measure a difference when you're looking at things like macro data, like temperature and pressure and stuff like that. That's the same thing. And so when you look at the number of ways that I can take a particle and swap it out like that, that's far smaller than if I took the particles and I uniformly distribute them through the cells and I started exchanging all of them.
Yeah.
Like the number of ways that the system can find itself in a uniform distribution of cells is significantly larger than if they're all crumbled together, like in the original example. Yeah. And so what that does is it takes mu space, and it says, okay, if I take mu space and look at all these different ways I can change them, and then I look at what that looks like in gamma space. What this does is this subdividing of mu space this way does a coarse graining of gamma space. Now, so think of mu space as being the triangle, and think of gamma space as being the composite Hilbert space. Yeah. And so what this does is it creates a coarse graining of gamma space, and of a volume in gamma space depends on the number of ways that I can rearrange this system. Yeah.
It's a high resolution, lower resolution kind of thing.
I mean, it's associated with the fact that it's associated with the fact that this idea of everything being crumbled up in uniform and being not uniform, that's associated with think of that as putting all the particles in a room, in the corner of a room. If you let it evolve freely, it's going to uniformize everywhere, and so that's a very low entropy state. So all the things, and so that low entropy state in mu space corresponds to a small volume in gamma space. And the uniform distribution represents the largest volume. And so when you allow a system that's in a low entropy state to evolve and uniformize, then its macro characteristics stop changing. So it's like its pressure and all these things and temperature, all these things start becoming constant. So that's called reaching equilibrium. Yeah. That's the thermalization process. The thermalization process is to start from a low entropy state. What was I saying? Yeah, so this idea of starting from a low entropy state and going to a high entropy state, where you reach equilibrium, that is called thermalization. And so what it looks like in mu space is that you start off from all the particles being in a single cell to them being distributed throughout the mu space. But what that looks like in gamma space is starting off from a volume that's small and moving to a large volume until you reach the volume with the maximum size. And that maximum volume represents equilibrium. Yeah. Because it's so big within Boltzmann, with arguments of Boltzmann, that equilibrium thing is so big, it takes up 99.99% of the space. So it's it's like the probability that the system will be found in that state is so high, and that's his response to Lockschmidt. His
Yeah.
response is these other things you say are possible, but when you look at all of the ways this system can order itself, those make up 0.000000001%.
Yeah. Yeah.
So the likelihood that you're going to see it is nothing.
Mm.
And instead, the likelihood that it thermalizes, and then once it finds itself in this larger state, it just floats around in there because it's almost impossible to get out.
Mhm.
Like the likelihood it'll get out of it is so low because it takes up 99.99%. So that's the main characteristic of Boltzmann's argument for the arrow of time, is that the volume of this gamma space of equilibrium is so large. And so what I've been demonstrating in my work is that when you look at my actual work and you look at these manifolds of purifications, they function as the macro states. They function as the coarse graining of gamma space.
Okay.
And the equilibrium macro state just so happens to coincide with maximum entanglement.
Uh-huh.
So what it's saying is that the universe evolves to maximize entanglement. And when you take this previous result of the fact that composite Hilbert spaces, and you look at the actual space, and the vast majority of it consists of maximal entanglement, as far as I could tell, no one has an explanation for that until I come up with my coarse graining. My coarse graining explains it exactly what's going on. It's thermalization. This is why I keep trying to tell people, it's like, I think what I found here is actually deep and profound. Like I really do think that I've discovered something that is very, very important.
Yeah.
And I need to communicate it to people.
But see, like Boltzmann did this whole argument, and he could have just, to me, it sounds like intuitively just that you have gas, you're right, like inside a box, they're on one side, and they go to the other side because there's like way more ways they can be distributed over the entire volume than in one place. That's why they evolve. So why do we have to do this whole argument to just say the same thing, isn't it?
Well, you have to prove it mathematically. He has to actually construct something quantitative.
That's what I want to get at. Like with you, what you did also is like, obviously there's going to be more entanglement as time goes on, right? Like intuitive.
Yeah. I mean, that's why quantum computers are so hard to scale, because the damn things decohere so easily.
Yeah. No, but that's what you're doing. That's what you're doing also, like mathematically, because intuitively it makes sense that things are going to be entangled more and more as time goes by. That's what I'm saying is true?
Well, it's the funny thing is that I didn't start off with the goal of doing the second law of thermodynamics, arrow of time. I started all this to study fidelity, because like I said before, the crazy thing about all of this is that the fidelity can be computed by looking at the surface, like looking at maximum overlap between purification states.
Yeah.
And the thing that really, so now going back to the triangle and the fact that you can rotate it, what you find is that when you're looking at the fidelity of quantum states, if both of the density operators exist on the same probability simplex, then everything is classical. There's no need for quantum mechanics. There's no need for purification. You just do a classical comparison of probability distributions, and you're fine. Like it's not hard at all. But what happens is that when you get the quantum appears when the density operators have two different eigenbases. So this goes down to the idea of taking the one simplex and rotating it. So now I have one fixed simplex. I have one density operator at a point over here. Then I have another one that's a point over here. So now I'm saying to myself, I'm sorry, go ahead.
Yeah, you went on too quick. So you're saying if there was like, what was the first case where it's like mimics classical mechanics?
When both of the density operators that you're computing the fidelity for exist on the same probability simplex.
Yeah. Now, what does it mean to change the eigenbasis? What does that mean? Like, I know.
Yeah. So in this case, the pure states are the eigenbases.
Yeah.
So the pure states are the eigenbases that represent the simplex.
Yeah.
And so to change the eigenbases is to take the simplex and rotate it. So I can do a
What does that mean?
I can do a unitary transformation to each one of these. So remember, going back to what that means, you have a Hilbert space. So remember the standard structure of quantum mechanics. You have the Hilbert space, and then you have the space of operators that are acting on the Hilbert space.
Yeah.
And so the Hilbert space itself is characterized by the symmetry group that maps between all pure states.
Okay.
So remember, I'm sorry, go ahead.
The system, that's how Hilbert space operates in the first place.
Yes, the Hilbert space itself is characterized by a symmetry group.
Okay.
And for instance, like SU.
So this triangle exists, like, so we're just rotating it. That's what you're saying. Okay, I get it.
Yeah, so specifically, it's like I was saying, like with a qubit, the symmetry group of the Hilbert space of a qubit is SU2.
Okay.
And so that's why you're looking at the Bloch sphere, the visualization of the Hilbert space SU2. And so when you're rotating the Bloch sphere, which is associated with going from a state, you're applying the symmetry group associated with the Hilbert space.
Okay.
And so what that means is that for each pure state, I can apply a unitary transformation on it, and because each pure state can be turned into an operator, a projector, like I showed earlier, then that means that I can always construct a set of orthogonal pure states. Well, I can always do that in either way. I can do that whether it's a projector or not, but there always exists a set of orthogonal pure states. And so the orthogonal pure states, those are the things that represent the simplex. So you need orthogonal pure states to represent a simplex. So those are easy to generate. Then what I do is once I generate one orthogonal eigenstates, so one orthogonal eigenstates that represent a simplex, I can just apply the same unitary operator to each one of those bases, and then that rotates the triangle.
Okay.
And so the thing about which is interesting, is that if the two density operators exist on the same triangle, then everything's classical, everything's simple, nothing's hard. But if I take one triangle and rotate it and have another fixed one, and then one density operator over here and one density operator over here, and I ask you what is the similarity in information, then everything gets entirely more complicated. This is quantum mechanics. I literally think that you can understand quantum mechanics from this perspective. Like, this emergence is quantum mechanics. This split is quantum mechanics. And the thing that's valuable about this perspective is that because I've diagonalized all of my density operators, that's why they're on these triangles. These triangles represent a classical object. So each triangle in itself, in isolation, represents a classical object. And the quantum appears in the unitary relationship between them. It's the fact that I can split them, which makes it quantum, which is associated with the algebraic structure that I mentioned earlier.
Yeah.
Because the unitary transformations are algebraic transformations. It's the algebraic structure that makes quantum.
Okay.
And so once you split them, and then you have one density operator over here and one over here, and you start asking how similar they are, not only does the mathematics get more complicated, you start needing fiber bundle structures, and the actual process for computing them is the same mathematics of gauge theory. You get the same mathematics of gauge theory. And this relationship between the lower dimensional space and the composite space, this is where all this, like, if you listen to Eric Weinstein talk about this is all fiber bundle stuff. And it's closely related to fidelity, quantum entanglement, quantum error correction, the Bohm-Aharonov. The Bohm-Aharonov effect is also done within the relationship between a base space and a fiber bundle structure. Like the richness of this is insane. And as far as I can tell, people are like it's this low hanging fruit everywhere. There's low hanging fruit everywhere, and I have so many calculations and so many things. Like I'm just drowning in possibilities of things to research. I haven't even gotten into the idea of perception and how these things, like I was talking to you earlier, and what I tried to explain in my video on the last video I posted on perception of physics, that not a lot of people didn't watch, but that's okay. Like I tried to explain to you exactly how this is just a matter of perception, because unitary. So the exact same thing I described in that video with the eyeballs is exactly what's happening with this.
Yeah.
So now you're getting into the nature of quantum, because if this split is what quantum mechanics is, then it's all a matter of this perception thing. And like the fruit is so low. The concepts are so simple because I'm treating everything classically. It's just a matter of rotating triangles. Spheres and triangles. It didn't require anything more than that. And what I find when I talk to other people, it's just like, I mean, some people, like my co-author, Carlo Coffro, he was so encouraging. He was like, this is like amazing, because it's this jump from fidelity to thermalization.
Yeah.
It was just by the fact of going like, these are macro states. Like this thing from here to here, the macro state, and I just like asserted that, like, this. What is the nature and the essence of like Boltzmann's entropy? Like, what's the nature of it? What's the nature of a macro state and a micro state? It's a many to one mapping. You have one thing which represents the macro data, and then you have many things that map to it, and the number of things that are consistent with the macro data tell you about the amount of ignorance, because if only you have is the macro data, then all of the things that appear that map to it have to be treated equally. The more there are, the more ignorant you are. This is entropy.
Yeah, yeah, yeah.
And to me, it's just like, how do people not figure this out? Like, it blows my mind, man. And I know why it is. It's because when you look at physicists and how they think, a lot like that profession selects for people who think very mechanically.
Yeah.
And so if it's not in the textbook, a lot of them don't think about, or they all cling to math. Like everything has to be focused in math.
Yeah, 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 yeah. And like I feel like people who think outside the box, they don't have enough rigor and to go deep into the math, and you know what I mean, like understand it
Oh
deep.
no, I know, I understand.
You
Yeah,
have,
it's definitely a trade-off.
you have both, you know. That's your strong point in this whole thing. You
But
have.
that's the thing though, is I'm insanely slow. I don't really have both in the same way. Like these other people I'm talking about, the quickness and speed that they can formulate and compute and do math is like
Yeah,
like 2 or 3 times faster than me.
I know exactly what you mean. Yeah.
So that means that it's not actually that I have both. I do have the deficit, and I don't know, but I am proficient. Like I do have the proficiency and skills to do the math.
Yeah, yeah.
And like my mathematical background, and nothing that differentiates me, I think, from most physicists, is that my background is in general relativity, computational geometry, and quantum statistical mechanics and quantum information, like that. And I've also done work in photonics. So it's like that is not common to have that big of a spread of experience. And so the reason why the surface of ignorance and stuff is so natural to me is because I'm just applying all the mathematics from differential geometry, what I did my thesis on. So most quantum information theorists are not versed in differential geometry.
Yeah, I think it's all about just putting. I think you have like insane ideas. Like that's it's very powerful stuff. It's just about more people taking note of that. You know.
Yeah. Yeah, I need to. I mean, I'm also a terrible self promoter. I have a lot of like, I'm not. I don't know. I mean, that's what I've been trying to do. Is like, how do I self promote this, get people excited, get attention and stuff, and I overthink things. Like I said, I produce things slowly because I'm always trying to overthink things, and it's very hard. And my mind branches out to a bunch of different ideas, so it's hard to find an origin. And so I'm constantly going, oh, should I do this? Should I do that? So there's definitely a lot of deficit and flaws to the way my mind works. But yeah. But I think a lot of those flaws and deficits are actually part of the value too, because it's the amount of ideas. And then, like I always say, to be a theoretical physicist, it's like there's this fun phase, which is a phase of speculating. Oh, it could be this, it could be that, and that's the fun part. And then once you speculated enough, it comes down to actually doing the math and doing experiments and stuff like that to then validate your speculations.
Man, we were talking. I think that's almost 2 hours.
Yeah, yeah. I think
20 minutes.
Yeah, I think this turned out really good.